Yep.
Okay, sounds good. So thank you. So what I'm going to talk about today is my third PhD paper, which I was trying to use mass conserving perceptron to build catchment scale neural network for rainfall runoff modeling. So I will first briefly talk about the overall background story, but mainly I would be talking about the papers. So now the community is moving very fast. I have been seeing people start working on using differentiable distributed hydrological model or land surface model. But if we are talking about a lump model, it means we treat all the input forcing, output stream flow, Bayesian attribute as kind of Bayesian average. Then there are two main ways of developing such models. So using the rainfall runoff as an example, we can build a simple ANN for a specific catchment. And this application can date back to like 30 to 40 years ago. Whereas nowadays people like to build one gigantic model by feeding the model a large amount of data sets. And if the data set are cross domains and input output are multi-modality or multi-sequence, then nowadays people like to call it foundation model, right? But in hydrology, it's essentially build one model for everywhere, like you feed the data from multiple basin into one single network. So a lot of this is based on neural scaling law, which saying that you need more data to train as the model size is getting large. But of course, if we go this direction, then it's very complicated to explain the internal functioning of the large networks regarding what they are actually learning in the context of rainfall runoff modeling. And actually, the community is moving so fast. Now people here at the Berkeley lab, they claim the state space model actually outperformed the LSTM and maybe others. But since scientific modeling often favors parsimony, so I'm focusing on the traditional approach, building location-based neural network. And I think this topic is also a little bit underexplored. So in the hydrological community. So that's the focus for today. So the solution we propose to balance the accuracy and interpretability is the mass conserving perceptron showing in the middle. It uses the linear reservoir as a backbone and replacing the time constant parameter in the traditional hydrological model with time variable gating functions. This is inspired by the recurrent neural network architecture such as LSTM. And the simplest MCP architecture has mainly three gating functions: the output gates GO, loss gate GL, and a remember gate GR. So our goal is to propose something like MCP, which is more interpretable than the machine learning-based model such as LSTM. And it's also more accurate than a physical-based model such as linear reservoir or other hydrological models. So in this MCP series of papers, we test the MCP at the Leaf River as proof of concept in the context of rainfall runoff modeling. And there are three parts of these efforts. So the first part is we focus only on the single node, single cell state architecture, and adding different hypotheses on top of this single node, such as multiple dissection, input bias correction, etc. The second part is we use the simplest MCP unit to build a two-flow path 310 KMA hydrological models, where we mainly propose 6 mass conserving architecture. And of course, in theory, we can also use MCP to build things like GR4J or Sacramento model or others. And sorry, and the third part is my main focus today. We basically use the MCP to form a neural network architecture. So originally, we only include a result for Leaf River, but today I will show some of the result at Campos US catchments. So just quickly go through a few important points of the first two papers. In the first paper, we found, the simple MCP architecture, which only has 7 parameters, can already be performed very well at a Leaf River. So as seen from this hydrograph, it can pretty well capture both high flow and low flow. And I think if I remember correctly, the KG is around 0.88 to 0.89. So the other advantage of MCP is it's like we can open a black box to see what the gating function is actually learning, right? So for instance, we assume the output gate is a function of the cell state governed by nonlinear sigmoid relationship. So for the output gate function at the top left, you see 600 millimeter around layer is the threshold for the system to release the water. And similarly, we assume that the loss gate is a function of potential evaporation governed by also a nonlinear sigmoid relationship. Eventually, the loss gate appears to be exponential shape as shown in the middle left, but it still probably represents the reality that there's more loss when the PT value is large, and there is less amount of loss when PT is small. So another advantage for model interpretability is you can see from a loss gate time series showing at the middle right. The actual loss vary with the PET, which is larger in the summer than in the winter, etc. And the last example is the two-dimensional remember gate at the bottom left. It equals to 1 to minus the summation of output and loss gate to ensure mass balance. Because it depends on both the cell state and the PET, right? So we can plot a surface plot. And it also makes the physical sense. So in paper 2, as mentioned earlier, we can use it as a basis to build a traditional hydrological models. For example, famous Haima architecture, which
Hey,
has
Yuan,
three.
I just have a quick question, actually.
Yes.
Could you go back to the previous slide?
Yeah.
So what's the intuition behind the exponential PET loss relationship? Like, are larger PETs underestimated in the data, or what is this graph saying?
So, well, actually, this is a really good question. I think for the first paper, we try to simplify things. So, I mean, give another example, you can also replace the output gates with maybe things like soft plus, so it can even better represent the hydraulic conductivity property. You can make more analogy to that, but for the loss function, I think I got what you're saying. Like this is just a pure assumption, a simple assumption, and we didn't really try other relationships like maybe piecewise linear or something like that. Yeah, but I agree with you. Maybe we should
I
test
see, I see.
more in
Okay,
detail.
yeah. So you're
It's just
assuming
a
that. For a second, I thought you were like you learned this function, but okay, yeah, it makes sense.
yeah. Okay, so where am I? Okay, here. So yeah, so the Haima architecture has three tanks, right? So surface soil moisture tank, routing tank, and groundwater tank. So here are the results. In the paper 2, we benchmark the MCP architecture against conceptual rainfall-runoff model and LSTM network. So each box plot represents a different modeling approach and shows annual scale KG values over 40 years period. So the optimal value of scale KG is at 1, so higher precision of the box plot means a better predictive accuracy. So for the time being, we just focus on the purple box. So we found that MCP HIMA-like architecture with three state variable shown in the center box outperform the Sacramento model on the left purple box. And the Sacramento model actually has six cell state, but we only have three cell state. And this our MCP based HIMA architecture kind of outperform the LSTM network with given the same amount of state variable and perform kind of comparably to the upper benchmark of LSTM, which has 5 to 6 cell states. But our architecture only has around 20 parameters, but LSTM have maybe 200 plus parameter for the 6 cell state case. So our model is more parsimony, but also sufficiently accurate. Because those successful experience, we are comfortable at a standpoint to ask the questions, which is, can we use MCP to form a neural network? Because according to the Kolmogorov neural network existence theory, a three-layer V4 ANN with a finite number of nodes in a hidden layer should closely approximate any multivariate functions. So the question we are trying to discuss in the paper are things like how many network layers, how many node, cell state, and links, flow paths are potentially sufficient to accurately model the input state output dynamics of a given system. And here I just want to mention that there is an update to the single node architecture for the third paper. Originally, I assumed output gate only depend on cell state and loss gate depend only on PET. But in the third paper, I add a cell state together with PET into the loss gate. But it's still a sigmoid relationship. So for the Joseph's questions, maybe we should put a more generalized, function. But the goal here is really, we try our best to maintain a parsimony. So we just keep a simplest assumption. And the reason why we put a cell state into the loss gate is because the system loss should not only depend on the PET, right, but also should depend on how much water in the tank in the system. So the figure showing in the middle is the box plots for the 40 years annual scale kg distribution. And the metric is optimal at 1. So since I made this change, I found low percentile years improve, and the entire distribution is also getting a little bit narrower, and also the trending is more stable. So I quickly check the hydrograph. It can capture high and low flow, and kg during the testing period is about 0.89. And we see now the loss gate in subplot B is the same as the remember gate, are two-dimensional. And most importantly, the gate are still interpretable and make sense to our understanding. For instance, the yellow color indicates a high loss gate value, which correspond to large PET and high cell state value. So we use this new version of the single node to form the following MCP-based neural network. Okay, so the two main case we discussed in the paper is the following. The first case is the distributed input hypothesis, showing at the left. And because the dataset in the Leaf River Basin is spatially long datasets. And the distributed input is the case we, for example, using a mass-conserving softmax function to distribute the total precipitation into different nodes in parallel at the input layer. So if it's a one layer, then each node can represent different spatial component of the catchment. So at the end of the output layer, we will have to sum all the outflow from all the flow paths to ensure the mass conservation at the network level. And another potential case for distributed input is, if it's multi-layers, then it's similar saying that we partition the watershed into upstream and downstream, right? So it's a way of conceptualize how the catchment looks like. And the second case is the distributed state hypothesis, showing at the right. So in this setup, the input gate value is fixed at 1 for all the nodes. Meaning, each node receives the full set of inputs, including the precipitation and PET. We arrange multiple NCP in parallel, allowing the network to form a more flexible and expressive function to approximate the rainfall runoff dynamics. So at the output layer, we apply a softmax function across all flow paths, which ensure that the resulting weights sum to be equal to 1 to ensure a mass balance. And this design of distributed state network is nice because it guarantees mass conservation also hold at a network level because the total output is weighty combination of flow from each parallel node and a weight sum to 1, as mentioned. So this DS hypothesis can be interpreted as introducing a stochastic representation of the system. So instead of modeling a single solar moisture state, we now represent a system with a number of parallel soil moistures. And another way, to think about this is each node is like an individual model, and the softmax weights determine how much the network learns to combine these models. So similar to how ensemble predictions are made. So I think in the machine learning community, this is called stacking. So anyway, so generally, this distributed state setting is similar to what Kolmogorov neural network theory, existence theory is saying, where we put multiple nodes in parallel and use function approximation to estimate the final output stream for each time step. So these are the two main hypotheses in the paper. But in the paper, based on the constraint of the weight in the input distributed layer and the linear output layer, we have 5 different possible cases for a single layer MCP neural network. I'm right now only talking about a single layer, and I'm using the 2-node case as an example. So the first is the DI case, as mentioned. In this case, the input precipitation is assumed to separate into 2 different nodes, each time set, but the sum of the precipitation from each node need to sum to equal to the total precipitation to conserve the mass. So in other words, the input weights are summed to 1, just like a softmax layer. And in this case, we assume each node represents different component of the catchment, so we just sum the outflow from each node to get a final stream flow. So the output weight in the distributed input case from each node equal to 1. And the second case is the DES case, as mentioned. In this case, the input precipitation mass is assumed to be the same for 2 different nodes. So the input weight equal to 1. And at the end, we combine the result using softmax to ensure mass conservation. And here for the third and fourth case, just like we relax the mass conservation at the network level. So the DIR case, distributed input relax, we make sure the weights are positive at the input gates, but not necessarily need to be summed to 1. And similarly, the distributed state relax DSR case, we replace the softmax layer and the output layer with the linear layer that all the weights are not really constrained to equal to 1, but the weights are positive. And the last case we call machine learning benchmark. In this case, we kind of combine the DS and DI and DS, and the purpose is to maximally relax the mass conservation in a reasonable way. So we follow the mass relaxation at both input and output layer. In the input layer, all the weights are positive, so that we will not get the negative precipitation. But at the output layer, we add one additional bias term, and both weight and bias allowed to vary between any real numbers. And this output hat layer then will be similar to the output layer used in any other machine learning models. So this slide summarizes the performance of single-layer neural network, including DI, DS, DIR, DSR, and machine learning benchmark MLB. And I put a result from 1 to 5 node. So some interesting finding here is the 3-node machine learning benchmark case provide the highest median year scale KG value and the highest worst year scale KG value. And the 5-node distributed input relax case provide the highest base year scale KG value. So if we don't look at the machine learning benchmark, although the high percentile years performance is improving, the low percentile years performance decrease either. So the distributed state case without the mass relaxation has the best worst year performance. And here I believe I picked several cases to show the box plot and the hydrograph. So to quickly report the key findings. So what we found is that the machine learning benchmark can better capture the flow peak compared to other cases. But it's difficult to predict the low flow, and this is because the output hat is the same as other machine learning model, right? That we could get negative value at a low flow because the weight and bias and the linear output layer can be any real numbers. And then so you have to say to 0 or something like that. So overall, I think one thing I haven't done, which is looking at maybe things like flow signature, and maybe we will have some other findings there other than just the scale metric. So in our paper, we explore more on the distributed state network. So we try to see if we can get more out from here. So what we found is, adding more than 3 nodes in parallel provide very limited benefits. Although you see the 5-node configuration slightly improve the performance in low percentile years compared to the 3-node case, it's it also lead to a slightly wider spread in the box distribution. So we feel like 3 node probably is the optimal. So from here, we kind of conclude that three flow paths in parallel are sufficient to capture the rainfall runoff relationship in a Leaf River. So another case, very important case for the single layer is we try where we allow a cell state information sharing among different nodes. So when I say information sharing, I mean the gates of a specific node can learn from the cell state information from other nodes. So for example, the output gate in the previous case is learned from its own cell states. But here the output gate can learn from not only its own cell state, but all cell state in the same layer from other nodes. So the output gate parameter was what was used to be a vector in previous case, but now it become a matrix. And according to the result, we found adding number of node up to 5 can be very beneficial than the case without cell state information sharing across the node. And this is saying that actually in Leaf River Basin, different component of the catchment is actually interact with one another. And this 5 node sharing network can be another way to conceptualize, but it's more difficult to interpret for sure than the previous 3 node non-sharing network. Okay, so here I show all the case, including DI, DS, DIR, DSR, and MLB with the node vary again from 1 to 5 for the information sharing case. In a paper, I ran this case by separating the experiment into 3 different types, including only allow output gate to share cell state, only allow loss gate to share cell state, and allow both loss and output gate to share cell state. But for the simplicity, I only show today the case allowing both loss and output gate to share information. So what we found here is overall, the distributed state case outperformed the distributed input case, especially the 5 node distributed state case has nearly the highest median of the annual scale KGE value, and sufficient well-performing worst years and narrow distribution. And it's actually up to these points when I conduct experiment, we mainly use the distributed state case as the main thread in this paper. So to emphasize how much performance is improving, I put a result of these 2 cases together with sharing and without the sharing. So the purpose is to show with cell state information sharing, the performance improvement is very obvious. And this information sharing feature is actually also embedded in the LSTM architecture. So the next thing here is to show the performance comparison of these 2 cases against the LSTM. As you can see, when a node increases to 5, distributed state, cell state sharing case show higher skill than the LSTM with the same amount of node. But here I'm just trying to show like the performance of our DS cell state sharing case is good, but not saying it outperform LSTM, because here is the case that it's very difficult to make a really apple-to-apple comparison. We know it's better to train the one LSTM model for the entire US, right? Or many continents with meteorological forcing and static attributes. But here our goal is not accuracy, but it's more like improving our understanding, right? So we training at a local scale, and in order to make comparison, we use the same input information, data splitting algorithm, and objective function, etc. But another issue is, previous research trend on Counter-Swirl LSTM is use mean square error or Nash-Scott-Clifford efficiency type of metric. And this metric is weighted differently based on the dry and wetness at each location. But here I'm using the KG as my objective function. So I think in the future, how to properly account for the aspect of taking into account the wet and dryness into the KG for the future Connors LSTM benchmark, I think it's something we have to think about a little bit more. Okay, so up till now, what I have shown is just the single layer case. But in the paper, I also try more than one layer. And for this multi-layer case, I only focus on the distributed state case network. Otherwise, there are too many experiments. So here is the three-layer network example with two nodes in the first layer, another two nodes in the second layer, and one node in the third layer. So according to the weight and bias value used between layers, we can have three cases in total. So the first case is the default, the DS distributed state case. In this case, the mass or the fluxes is conserved between the layers. So for example, if you look at a node at the top of the second layer, the input is the combination of the outflow from the two nodes in the first layer. And the weights need to be summed to equal to 1 to ensure the mass or flux conservation. So the hypothesis is, the outflow from each node of the first layer represents the internal flow, and then we weighting the outflow from each flow path in such a way that the summation of the weights equal to 1. The second case is the distributed state relaxed case, meaning these weights are positive but not necessarily summed to be 1. And then we have a final case, machine learning benchmark. And these weights and additional bias can be both positive and negative. So I'm not going to the detail of the math, but we can come back at any time after the presentation if anyone is interested in or have questions. Okay, so here, this is a very complicated figure, but let me walk through it. So here are the results for multi-layer distributed state network. We ran a network with the combination of 1 to 3 layers, and each layer allows maximally to have 3 nodes. So we organize the result into 3 blocks, from left to the right, with the number of layers increased from 1 to 3, and the cell state number is increasing. The 3 panels from the top to the bottom refer to the case that different linear transformation layer is used. So the top is the mass conserving softmax layer. The middle is the positive weighting mass conserving relaxed linear layers. And the bottom is the machine learning benchmark. So the weight and bias in a transformation layer or the output layer can be any real numbers. It's basically what I showed in the previous slide. So we use the same color for the box plot given the same cell state number. So what I'm trying to show is that the box plots with the red color mark show the best performance, which is the 2-layer case with 3 nodes at each layer. And if you remember the distributed state result for the case without information sharing, we only need 3 nodes for a single layer, right? So this is kind of saying that in Leaf River, we do need 3 flow paths, and each flow path may only need 1 extra flow routing. Okay, and here I'm showing the same plots, but using a distributed state case, allowing for the cell state information sharing in the output and loss gate. And it's clear, we only need 1 layer and not even the 2 layers, which in my opinion, kind of explain why most of the LSTM network model for rainfall-runoff modeling only need 1 layers. So the overall conclusion we draw here is, adding node in parallel is more important than adding layer in depth, and allowing gate to use cell state from all other nodes is super important. And because we are adding both number of nodes in parallel as well as the layer depth to the MCP neural network architecture, here we did something similar to the LSTM. Okay, so but we only test the case where each layer contains the same amount of node. So similar to what we found for MCP network, adding depth is not really useful either. Oh, by the way, so last year I also tried the case by removing the information sharing feature in LSTM. So in LSTM, there are gates for inputs, output for gates, and cell state update. So there are four weight matrices, and I change the matrices of these parameters to become a vector in LSTM, and I try different combination of removing this interaction and a number of nodes in parallel within a single layers. But the result, if I remember correctly, was kind of arbitrary. So I didn't really include in the paper. Okay, so after I have done so many experiments, it's actually very clear that the HIMA or any other hydrological model can also be viewed as a type of neural network. So here I list four architecture we propose in the paper 2. This architecture have multiple cell states because they have more than one node. So as you can see, MA3 has soil moisture tank and a surface routing tank. MA4 soil moisture tank, groundwater tank. MA5 is like HIMA, so it has soil moisture tank, surface routing tank, groundwater tank. MA6 is similar to MA5, but we have one extra surface quick flow path to properly account for things like overland flow. Yeah. And so, we treating those hydrological models as neural network and allow them to share information in the output gates. Because if you look at the equation, in the hydrological model, the loss gain in the hydrological model does not depend on the internal cell state. So that's why we only allow the cell state information to share in the output gate for within those hydrological model. Okay, so in this figure, the pink box plot in the first block are the four HIMA-like architecture without information sharing. And the red box plots in the second block are these four architecture I just showed in the previous slide with information sharing. So the cell state in the service tank is sharing information with. So in the output gate in the soil moisture tank is determining how much water release. Also depend on the cell state in the groundwater tank and the surface routing tank. So yeah, so that's the idea. So we can see the red perform better than the pink, and also outperform our distributed state MCP network when the information sharing is close. But for those MCP, for this HIMA-like MCP architecture, although it can outperform our MCP neural network without information sharing, but it cannot really outperform the MCP network with information sharing as well as the LSTM. And I think this is because those hydrological model, the tank, they are arranged in such a way like it has so much physical, the regularization is so strong, so it cannot really outperform the neural network, which has more flexibility. For example, if the HIMA is more like you have maybe one node in the first layer, but groundwater tank and the surface routing tank is the second layer, has two nodes, and which I showed in the previous experiments. Actually, 330 is the best. 120 may not perform that well, so that may be the reason. But anyway, so the point here are that probably different components of the catchment are also interact with each other, so that this information sharing feature can be so useful even in the hydrological model. Okay, so the last experiment at the Lip River is the network pruning. So the idea and the focus is to see are there still any redundant components after the network has been developed. So here we have 5 blocks of box plots. The first 2 blocks on the left correspond to the distributed state case. And the subplot A shows the performance of a single layer network as the number of nodes increase from 1 to 5. Okay. And in subplot B, we take the 5 node case and progressively remove the flow paths one at a time. So the leftmost box plot in the second block correspond to the case where one flow path is removed from a 5 node network. The subplot B box plot shows the case where the two nodes are removed and so on. Okay, so you see the performance is decreasing. So we found remove one node slightly improve the performance. Since we train on the KG scale for the entire training set, but we calculate the KG annual for the box plot. So it could be this just happened by chance. And in subplot C, we show the performance of the information sharing distributed state network as the number of nodes increase from 1 to 5. So you see the performance is increasing. But in subplot D, we progressively remove flow paths while maintaining the entire internal parameter structure, including those used for sharing cell state within a gates. So as you can see, the performance remain very similar to the unpruned 5-node sharing network. So here is like in subplot D, we take this model, the last model in the subplot C, and then we start to shut down the flow paths. But you see the performance does not really decrease that much is because I didn't really, now the output gate parameter is a matrix. And the diagonal represent the parameter control the output for its own node. But I didn't really take away when I say take away, I mean set the parameter to 0. I didn't really set those interaction term to 0. So you see, we only shut down the flow paths. So the performance at the beginning, even you remove 1 flow path, 2 flow paths, or even 3 flow paths, actually the performance does not decrease that much. Okay, but if we go to subplot E, which meaning that we not only shut down the flow paths, but we also turn down all the parameter for the interaction associated with it to 0, then the performance stop dropping. So I think the conclusion I got from here is like, I think this is really interesting because the subplot D, this case basically saying that the cell state still performs some kind of function to contribute to other flow paths, right? So it's more like you have multiple network and you use one network to learn the parameter for another network, but this network does not really contribute to the outflow. But okay, so another interesting point here I want to bring is I only do the network pruning, but I didn't retrain it. If you look at the literature, when people remove rows, when they do the network pruning, they will do the retraining. But the reason I didn't do the retraining was because the distributed state network, the output layer is the softmax. So which means you have to define 5. For example, if you have 5 nodes, you have to define 5 parameters first. And then you take the exponential and then you sum them together, put in the denominator. And then your numerator will be exponential of one parameter. So once you remove one flow path, I have no idea how to reorganize those way to be the same as before. So that's why I didn't do a retraining. But anyway, I think it's something that maybe we can explore a little bit more if anyone is interested in this. Okay, so another thing we try in the paper is to explore internal functioning of this network formed by the interpretable MCP units. Because I think the sharing case is too complicated, so we plot a non-sharing case for a distributed state network. We plot the output gate based on order of the maximum value of the output gates. And since one of the conclusion we have is for the non-sharing case, 3 nodes is the optimal for the Leaf River. So we dive deeper into these 3 nodes, no cell state sharing distributed state network to see what interpretation we can get. Okay, so here we plot different internal time series for the purpose of deciphering what model is learning. So each column represents a result for different years, including dry, medium, and wet years. And those years are determined by the flow peak of light years. Okay, and I put from the left to the right. And each row represents different variables. The top row shows the observed stream flow hydrograph. Second, fourth, and sixth rows shows the corresponding cell state, output gate state, and the accumulated component of a stream flow. Third, fifth, and seventh rows shows the same value as in rows 2, 4, 6, but I plot a fraction of their total value. Okay. So for this three node case, the three flow paths can be kind of interpreted as representing a slow responding groundwater flow path, which correspond to the blue color with lower, maximum conductivity and moderate yeah. And then the other is like the moderately respond internal flow path, which correspond to the orange color with intermediate maximum conductivity and quickly responding surface flow path, corresponding to a yellow color with higher maximum conductivity. I mean, we can always come back to this slide later after I present, but the overall idea here is you observe the magnitude of the cell state in each node, then we will know if the gate is being activated based on the output gate I just plotted in the previous slide, so that the flow path can release water. And then you try to see the proportion of the flow contribution from each node, from each flow path, and see the magnitude and see if it happens at a rain-driven period or not. And then you make your interpretation. So our interpretation here is like, we have one surface flow path and two subsurface flow paths, and we interpret the subsurface flow path, one of them as in interflow, and the other is like groundwater flow. But let me know maybe if you guys have any better interpretation. We can come back to this slide if necessary. Okay, so here, actually, this is one of the reviewer suggestions. So to test on multiple locations. So here I took the CAMOS US 513 catchments from water year 1982 to water year 2007. So based on what we learned from the Leaf River, I first run and compare the single node versus single layer distributed state 3-node case. So without information sharing. And the figure from the left to the right are scale kg and 3 component of the kg. And for the time being, we only focus on the scale kg. Okay, so we see the improvement appear at the southwest and maybe Missouri and north part of the Midwest. So this is kind of saying that this catchment within those area require more than one flow path. And then we turn our attention to compare this single layer distributed state 3-node case without information sharing against what we found the best in the Leaf River, which is the single layer distributed state 5-node case with information sharing among loss and output gates. So we found several basins at the West Montana's US start getting improved, but the place like South Texas, the scale is decreasing. And I think the improvement at the mountain west is because the model architecture is getting complicated. So several basins can learn the right thing, maybe for the wrong reason. And the performance drop at the Texas just means, we misrepresent what's happening in the catchment. It may not make any sense to assume there are 5 different components of the catchment are interacting with each other. Maybe just like groundwater or something else is more important and is dominant hydrological response over those locations. In this slide, I show the result for relaxing the PET constraint for a single layer distributed state 5-node case with cell state information sharing. So the original one with PET constraint is showing at the top, and the one relaxing the PET constraint is showing at the bottom. So for the result I have been present up till this point, all the nodes are also has this PET constraint. So which meaning that although we allow the loss gate to learn from the PET, but at the end we calculate the loss derived from the loss gate, and then we see if it's go over the PET. If it's go over, then we change our low scale. We turn out a low scale value, but now we relax this constraint and then we compare the results. So we see something very interesting at the Western mountainous US. The performance improved a lot. You see many locations, the color turns red. That means they approach towards the optimal, scale KG at 1. So the hypothesis is here is, because this basin, most of them contain the permanent snow across the years. So the relaxation of PET constraint gives the model more flexibility to account for the erroneous mass balance within this catchment, because the current MCP does not have a snow module. And this can be further confirmed with the comparison shown here. So in here, I compare this 5-node case with PET constraint relaxed against a single layer 5-node LSTM. So the key difference between these two architecture is that, my 5-node network still preserve the mass in a nodal level, not a network. Yeah, it's still conserve the mass in the network level as well as the network level, but the LSTM is completely non-mass conserving. And we found, LTM did an even better job in those western mountainous region, especially at the catchment near the south. So I probably will have to check further as I'm doing a large sample study right now and see if the original poor skill is coming from the things like we need a module another cell state to account for the groundwater errors area. And this is a result for the CDF curve. The best case we have now is the single layer distributed state 5-node case with information sharing and PET constraint realization. So the median of the scale KG across the country is about 0.86, where the 5-node single layer LCM is about 0.89. So I'm currently adding a snow module to the MCP and also play around with the ways of initializing the weights. So hopefully the result can be closer to LCM or even better soon. So here I found one catchment near Sierra Nevada to further explore the performance and the interpretability. Because this catchment has snowpack during the winter. So you see from the box plot at the left showing the annual scale KG distribution, like the 5-node case with information sharing and PD constraint perform pretty bad compared to the same architecture, but relaxing the PD constraint. But I mean, what makes me feel interesting is that the single layer 3-node distributed state case without information sharing is actually perform pretty good, as nearly comparable to the 5-node case with information sharing and PET realization. So I'm guessing it's because this representation fits very properly to what is actually happening in this catchment. Maybe 3 cell state represents snow, surface flow, and groundwater flow individually. So and there is only a very minor interaction between each of them. So the cell state in each flow path does not affect the release of water at other flow paths. So I use these 3-node distributed state, no cell state information sharing case to explore the internal functioning again. So here I plot the output gate and it's different than the case I showed previously. Here the color is coded in the order from the largest to the smallest. So we see the first gate activated coding in blue when the internal state is probably around maybe below 100 millimeter, and the maximum gauge value is about 0.7. Second gate coded in orange start activate around maybe 500 millimeter with maximum gauge value to be around 0.4. The last node has a very small value of activation, and it only release the water when the cell state exceed around maybe 400 millimeter. So here from a subplot, D to F, we see that the basin experience accumulation of snowpack in all three of the years. The original snow fraction value reported in the camels in this catchment is about 26%. So it's kind of a snowy catchment, but not. I don't know whether we will say it's a dominant snow dominant catchment, but it is a snowy catchment. And from subplot G to I and J to L, we see larger peak value for the output gate correspond to smaller magnitude of the internal cell states. The output gate of the first node, the blue line, consistently show the highest activation among the three nodes. It dominates the output gate ratio from around August to roughly January in each of the years, as shown in subplot M to O. And this is consistent with the accumulative stream flow plots from subplot P to R, where the first node provide a larger portion of the stream flow output. So our interpretation here is that the stream flow output from the first node represent the dominant response to precipitation inputs. Subplot V to X represent that the second node in orange provide almost no flow contribution during period July to January, and instead contribute primarily during the January to July. So one possible explanation is the cell state of the second node represent a snow water equivalent. So with a contribution to stream flow corresponding to the early spring snow melts. And because snowpack exists primarily between January to March, so based on the blue line, in subplot D to F, we see that the snow occur mainly between January and March. And further support for this interpretation come from the output gates of the second node activate only when the internal cell state go over like around maybe 400 to 500 millimeter. So if we see the cell state from the subplot G to I, only during this period, the cell state in a suite in orange have several months go over this threshold, so the node can release the water. So that's why we are interpreting this as suite, because the release could be interpreted as a snow melt here. And finally, we found, although the third node has a very small output gate peak value, it maintains the largest overall cell state value among all the nodes. And this correspondence of a small conductivity with a large cell state. So if we see the log scale subplot S to U, the yellow line contribute constantly to stream flow, and the only exception can be found is only at maybe for a very short period around December of the median and wet years. And in a subplot T to U, this kind of suggests the third node yellow line primarily represent a snow draining groundwater and maybe base flow system. I think it's a little bit hand wavy, but that's why we try our best to interpret those results. And that was actually the last slide of the paper, and I don't really have much to say about the conclusion right now because there are still ongoing work. I'm covering MCP with simple simple snow tank, and I'm testing a single node architecture across the US right now. And we also include these two references in the papers, in this series of paper to highlight the importance of identifying the parsimonious model architecture for each catchment. And the best is we can automate in this process if possible. And hopefully one day I can get to this direction. So that's it for today. I will stop here and take questions.
So are we basically slowly moving towards like basically a differentiable mod flow model or something? It's like fully distributed, physically based, but kind of learning from observations. Like, I mean, I guess you can push this complexity until you basically have like 1 meter by 1 meter grids,
Mhm.
along the whole catchment, right?
Yeah, so right now the model is still catchment scale, but I mean, once we learn from each catchment scale, then probably we can determine what's the minimum complexity for the Connor scale, right? So, and then we build a Connor differential model, and then we add other component to it. Right now, Snow
Oh,
for
I'm
sure.
not re Yeah, yeah. I guess Connus, yeah, makes sense as well. But what I was basically saying is just within a catchment, you discretize,
Oh, yeah.
I message you. By 100 meters by 100 meters or something. Um,
Okay, got you.
yeah.
When
Hi,
you
John.
add like, oh, go ahead.
Uh, Thank you. Quick question. Can you remind us how do you define information sharing?
Oh, so maybe let me start by showing this. So in a single node, right now is the case at the right to form the neural network. So in this single node, you see you have input gates one, you have output gates depending on cell state, you have loss gate depending on PET and cell state. Um, but when you put a node in parallel, you will need, for example, the distributed state case, you will need a linear output layer to combine the result, right? So the simple case will be, yeah, like this. You put all the node in parallel, and then you go through a linear output layer, and then in machine learning, this is you have weight and bias, and it can be any real value. But here I just use a softmax to ensure the mass balance at the network level. And the default case is each model just do the things by itself. But for the sharing case, it is okay. Maybe sorry. So they do the thing by themselves, meaning the output gate learn from the cell state. For example, the top node, the output gate of the top node learn from the cell state within itself. So you define a GO1, a sigmoid, a bias term plus a weight and times the cell state, right? In the first node. And then
Right.
you release your water. The cell state times the gate value, it determine how much water outflow coming from the first node, and then you times the weight W1 out here, and then
Mhm.
you do the same for second, third, fourth, and fifth. But for the information sharing here is like for the first node, the output gate is a bias, but is uh, a parameter times the cell state in itself, and then another parameter times the cell state in the second node. So in the first case, the parameter in the output gate is 5 times 1. But here, the parameter in the output gate is 5 times 5. Because the cell state in the second node, third node, fourth node, and fifth node, it will also determine what the final output gate value is in the first node. And then the same for the second, for the third, for the fourth, and the fifth.
So basically, a change in the information sharing is based on the change in the architecture of the algorithm,
Yeah. So you change your
pure
architecture,
architecture.
yeah, in a way like the output gate has to take the information from other node to decide what my output gate value is. Yeah.
I see. And do you maximize something to see if you are getting the larger amount of information by doing that, or what is the reason why you want to change the architecture?
Oh, because so if you think about all these different component of the catchment, it kind of saying that the groundwater state sometimes will influence uh the release of surface water. So I mean I guess we can have other hypotheses like oh not it's not full sharing but maybe partially sharing. Yeah, so but anyway, so that's why I try the node from 1 to 5, right? Because if you have two node,
Right.
then this is 2 times 2. And I actually try more, but the result does not improve. So I think after
Mhm.
5, it's kind of saturates. And
Mhm.
I don't have a really good explanation on that, on why that happened, because I guess this may vary across different locations. But we just kind of learning something in the Leaf River and then try to zoom out to other location. Otherwise, there are too many cases.
Right. Thank
Yeah,
you. This is great work. Thanks so much.
I think.
I have a question about, some of the things like when we change the architecture a little bit, or you're like interpreting some of these components as reservoirs or flow paths. Do you
Uh-huh.
think that we are actually approaching like a truer representation of the physical system?
I think I think you have a paper with maybe one of the student in Alabama, and I think you guys' idea is more like distributed inputs. You are
Hmm.
kind of using different tank to represent different part of the catchment, right?
Yeah, yeah.
Uh, yeah, so I mean, I guess this something we can try, but we also will have to have some measurement in the catchment, so we know how to properly conceptualize uh the entire architecture. So right now, because I didn't go to Leaf River, so I don't know how the Leaf River looks like. So I
Mhm.
just conceptualize with hundreds of architecture to see which one works the best. But maybe if in
Mhm.
a case you have different, say, distributed stream flow data, then maybe we can know,
Mhm.
how maybe put one node in the upstream, three node in the
Mhm.
middle, things like
Yeah.
that. Yeah.
So when you let's say you stumble upon a configuration that works better,
Mm-hmm.
would you expect that that configuration, even if you didn't plan it, would you expect that that configuration is a more accurate representation of the physical system, or is there like one thing compensates for another?
I think there must have some compensation even for a really good model, but I think the best way we try to do is if you are talking about more scientific model, then you have to find the first major component, right? And then you make that a priority to approximate and to conceptualize.
Mm.
So let me see.
So
Yeah.
it's kind of like a first order response, second order response kind of a
Yeah,
thing.
yeah. Because we are adding complexity based on what we need right now. So
Mhm.
it's not it's not like a deep learning model you one feed to the O, but it's like I said at the beginning of the presentation. So if you go back to 30 to 40 years, they are building ANN in one specific catchment, right? But
Mhm.
now because people are focusing on large network. So one model
Mhm.
for everywhere, but it's less interpretable. Um, and actually, I mean, in my opinion, I think we have to explore more in the first direction. Otherwise, I don't know. I mean, because we still need to have some domain type of methodologies, not just apply algorithm and then run it and then yeah, interpret what the computer science is focusing on. Yeah.
Mhm.
So
I guess ultimately, I'm wondering if we can use this to derive some sort of not even interpretable learned model, but like derive like an actual formulation that we would consider true.
You mean when you say that are you saying for one formulation for every catchment or like
Or just
different?
in just take one catchment,
Uh-huh.
try these formulations, try the architectures,
Mhm.
and then use that like, okay, if this one is what's working best, like then we can assign, an actual like maybe write down an equation that we trust that is somewhat representative of the physical system.
Yeah, I mean that will have a lot of work to do. I guess what you're saying is like maybe eventually you have 500 catchment in the US or maybe thousand of catchment around the world, and then you will have a map, and then you will have different category, which is
I'm just thinking about like like can we truly come up with the the physical catchment
Mhm.
response in like some sort of like closed form?
Closed form. Oh, I don't know. I have to think about it. Yeah.
I don't know either.
So if you
But
have idea, we can
that's
change.
just,
Yeah.
yeah. And I guess that's always where I hope this work is going.
Uh,
I think I have the same question. Where do you think this research is going?
Mm.
I haven't think that long yet, but uh, I'm doing large sample study right now. So right now I'm focusing on a single node coupled with snow, and then actually the result is similar to. I think I got if we only select the base model, I think the median scale gauge is about the same as the result I just showed. Is about 0.86 or 0.85, but there are lots of hypotheses we can test. Um, so I have some other ideas about maybe but my idea is more about the on the modeling side. Yeah. So I have a lot of idea about how to build different network architectures at this moment, but don't really have others at the moment. Yeah.
Can I ask a question?
Sure.
You might have kind of like talked about it, but I kind of probably missed it. What is the lag that you use to the models, to the LSTM models, and to this one?
What lag?
The
Oh,
lag of precipitation. Yeah.
you mean the sequence length?
Yeah, the sequence of input. What's the lag number? Like the look back period.
Oh, I think it's 390. Yeah, I mean the input is precipitation and PET because I use the same input for every model, but
Yeah.
uh I try different sequence lengths. I think I eventually use 390, yeah.
Okay. 390. And one other question I had is that why, I mean, I do understand you wanted to make apple to apple comparison, but like 3 nodes for the LSTM, don't like if you increase the nodes, would you expect the performance of the LSTM change or not on these catchments?
Uh you mean the locally trained LTM or the Connors LTM?
I mean, you showed a lot of results, but like eventually, like when you were talking about using 3 or 5 nodes for the LSTM, that
Mhm.
was I'm not sure which experiment because there were 2 or 3 papers that you kind of covered all of them. But I
Oh,
was
so
wondering, yeah.
okay, so let me answer it first. So in for this series of study, I only train LTM locally. Uh and I think I tried a node from 1 to 10 for a single layer, and I found 5 or 6 is the best. So that's why I put a result for either 5 or 6.
Okay.
And I do try adding more, but not really helpful. Yeah.
Okay. So my last question is regarding like the efficiency of deployment, because in my in my own experience, like doing any kind of recurrent neural network design, because it's not really optimized for CUDA based on PyTorch or TensorFlow, it takes a lot of time to train and optimize. I mean, the nodes you use have an impact, but I was one, and also like, of course, the lag has an impact. But did you see like a considerable amount of time difference between LSTM and what you propose in training and also deployment phase?
So actually, right now the model is LAM model, so which meaning I run at a catchment scale. So actually, all the result you see today, I only run on CPU, and this is because the MCP you have 40 years data, right? So you just run one for loop, and for the epoch, so you only have one big batch size because the model has to run for the entire 40 years. And then, so the sales state can be physically meaningful, right? For each catchments. And then I think we use a data splitting algorithm called MDuplex. So meaning we try to make the training, selection, and testing set distributed equivalent as possible. And then we run the 40 years, and we only calculate the time point at the training set. So I actually try my model using GPU and not using GPU, but actually does not affect that much. I remember when I first time, maybe 5 or 6 years ago, I start running LCM. I know using GPU and not GPU, the computational time is like 20 time difference. But it's not in this case because I think the most time consuming part is calculating derivative. And because in LLCN, you usually train on a large number of data sets, so you have a lot of batch. So that's why it costs so many time. And also the I/O it also could cost the training time. So, but I understand what you're saying, but it's just not the case. I reported here. Yeah.
Oh, thanks. Maybe one or two very quick questions as well. So these LSTMs usually have problem for very small catchments. Have you like when you compared, have you seen like a significant improvement over very small catchments or no? Because that's basically like the differentiable model developing Xiaoping group also showed huge
Oh,
boosts over.
you mean okay? I actually don't know this, but if I can repeat what you are just saying, you say in a small catchments, LTM will
Yeah,
have.
so like I mean there is a range like when the catchments get very small, LSTMs are not able to capture the dynamics. That's at least in the lumped procedure. I was wondering if you have like when you compare the results to like a regular LSTM, seeing how the performance is diversified against different catchment properties. I mean, are yeah.
Go ahead. Go ahead.
Yeah, and the other one is one other thing that like LSTMs kind of like this is the problem of LSTMs in general, and then the where they are very good is understanding complex patterns. So like in ungauged like syntactic ungauged catchments, they show better performance over calibrated hydrologic models. So I was wondering if this is also something you have investigated or are you like planning to investigate?
So for the first question, I don't know that before you saying it, so I will check. But
Actually,
I
I did quite a lot of investigation into catchment size, and you're absolutely right. But every model that I've ever tested also does poor, the performance degrades the smaller the catchment size. So this includes like standard lumped conceptual models calibrated to smaller catchments, the performance is highly correlated with the catchment size.
This is basically what the project I'm working on. So I was wondering if this could be something we could look into as well to incorporate.
Have you found any types of models that don't degrade as much or anything like that?
I mean, we were like what we have found out is more data, more high quality like data in any way. Like for example, we were kind of working on data integration with the national water model, and the model that was developed with within like Pacific Northwest National Laboratory to kind of integrate it with the LSTM. That's something we were working on, but our performance of like the LSTM models or even transformers, whatever we have done, are not good. And even like the raw national water model is also very bad. So what we have found out is we kind of like need a meta model to combine these. That's where we're standing at this point.
I'm sorry to take over, Yuan, but I think that these types of investigations, looking at where like the biggest failure cases are, I think that we need to try to do more investigation into where like all models are performing poorly for some reason. And I think that's great that you're working on that. Thanks for sharing. So I'm very interested in that as well.
Yeah, we should talk more about that. I don't know that much about that. Yeah.
I think Joseph, you're on to something too. Good point. Sorry, there was a second part of that question that you were going to answer.
Yeah, I think the second part was like, have you looked at like looking at the scheme of like the donor procedure to investigate like synthetic ungaged basins, because that's also something I think is relatively under investigated with these deep learning models, and a lot of people are overhyped about their capabilities.
Is Joseph still here?
I think he can't talk because he's been chatting.
Huh? What happened?
Yeah, he's here, but he cannot talk. Maybe there's people around, or he hears and he can respond in the chat, but he won't talk.
Because he asked a question and I forgot what I did. There are so many figures. I have to check.
He asked a question about the second paper and
Yeah.
the outputs. You can read it in the chat, Yuan-Heng. It's all written in the chat.
Yeah, but I don't remember what I did for that, so I also have to check. Figure S6. Uh-huh. Your output makes sense in this paper. In the second paper, it seems less interpretable. Did you change something about model here? What the difference? I think I didn't change anything, and let me see. Oh, wait. So this is the internal functioning for the. Oh, I plot different things. Here I plot a 3-node network which put in parallel. But in the second paper of the supplementary material, the figure 6 was the MA5 architecture, which is you got a soil moisture tank, you got a surface routing tank and groundwater tank. So I think just two different cases. Oh yeah, and I mean it could be just the MA5 groundwater tank. Maybe it's not the best representation to represent the groundwater system in the Leaf River. And we apply it, but we didn't. I think that's a little bit detailed, and I agree what you are saying in the review comments, but just that's just what it is. For from a result perspective, I mean, I use MCP to build MA5 and I apply MA5 to Leaf River, and then that's what I got. And maybe the groundwater tank need more improvement because right now in the MA5, the groundwater tank is essentially the same as the surface routing tank, including all the, you know, gating function shape and the complexity. But we all know that the surface routing responds very differently as compared to the groundwater system. So maybe that is something, I should also keep working on to improve the groundwater representation. Yeah. I guess. Okay, I guess I answered that. So, is there any other questions?
I'll just say great presentation, and it's always fun seeing your work.
Oh yeah, thank you for joining. Yeah, we should chat maybe in AGU or if you have time. Yeah.
Yeah, we should all get together at AGU.
Yeah.
Well, thank you everyone for coming. I think we will stop here as there is no more question on this presentation. Yeah, thank you again, Yuan-Heng, for